Okay, we wait for some time to people get here. Today, our first lecture, so I will make some kind of review at certain point. Do you have any questions on the last lectures or on the course? We had only one response regarding what you would like to hear today. So today is our last 4 hours. So I hope that you will get some things from this course for your future work. Maybe even well, something you will want to work on some of the problems which were outlined here. So there are 6 people at the moment, which is telling me that we need to wait a little. So we will, according to the request which I got, we will start from considering polymers. So we will consider some questions about rheology and then this system. We will see that in fact it's in order to understand the system, it's useful to consider an auxiliary problem of actually passive scalar field, which decays linearly, and it would help us to understand what happens with this system. So we are considering interaction of polymers with turbulence. We introduced a macroscopic field, which in fact is very similar to the local field of major stretching directions. And it interacts with turbulence because local amplitude of that field reacts on the flow. So the flow wants to stretch things in certain direction. However, that direction resists because it's elastic. And then we get a non-trivial interaction of inertial and elastic degrees of freedom. So inertial degrees of freedom want to develop stretching in certain direction, and elastic degrees of freedom reduce that stretching. So, well, we are really not many people here. All right, so so as you can see, this is some point which actually Nikolai raised in one of our emails, that polymers look very similar to magnetohydrodynamics. In fact, they are. You see that this equation, so we simplified it. In fact, this is not the last version of the equations which we had. So we saw that actually the Navier-Stokes equations are simply the same as the equations of magnetohydrodynamics, and the only difference is that the term which is responsible for the decaying processes for decay of B is linear term and not Laplacian term as in magnetohydrodynamics. So the consequences of this analogy are not yet fully explored. So the spectra were not consistently compared, and it certainly would be of interest. What we can tell is that there is a difference because, as you can see, in the steady state, where roughly speaking B must be kind of constant, I will quantify these things, of course, you need that the right-hand side is roughly 0, which means that grad V must be of order 1 over tau. And it's then very simple to see what happens with these equations. So if grad V is much smaller than 1 over tau, then B decays to 0, and the fluid behaves as Newtonian fluid because B is 0. Now B equals 0 is a solution of the equations. In the same way as in magnetohydrodynamic equations, there's always a formal solution unless you have some way of enforcing the magnetic field. You can have a solution B equals 0. The issue then if this solution is actually realized, which means if the solution is stable. So this is one of the reasons that we are interested in considering the behavior of small fluctuations of magnetic field in conducting fluids, is that you always have the solution with zero field, and then you want to see if this solution, if small fluctuations would grow or decrease. So, well, there's really not many people today, including the organizers. So I guess something is, well, the organizer, okay. Well, all right, I hope that everybody is well. It's not that everybody got sick or something. It's been a long course. So since we are in this, well, so there are always advantages to most things. There are disadvantages and advantages. So the advantage which we have at this point is that since we are so small a group, then maybe you can directly tell me what you would want to talk about and what you want to see in the remaining hours. I do hope, of course, that we will be joined by others. However, let us see what happens. So David requested that I consider in more detail these issues of whether you can have this range where the back reaction of polymers on the flow happens when in the range between full lengths of the polymer molecule and the coil size. So as we considered, you need for that number of monomers is at least 10 to the power 4. So it's not obvious that this range can be, so there are polymers with N which is of order 10 to the power 4, or even somewhat higher. So that is not a problem. And David indicated that it seems kind of realistic to create this in a laboratory. So the issue then would be if it's weathered. So what are the phenomena which you would see there? So the phenomena are that you will be most probably able to test directly the theories, which is maybe not of your main concern. However, the main thing would be, I believe, that you will be able to see the same drag reduction phenomenon in this, and you will be able to see what's the maximal drag reduction which you can achieve in the laboratory or in the field with polymers. So from the very beginning of studies of drag reduction, it was obvious that sometimes you get that there is kind of range of variation. So roughly speaking, people tell that drag reduction which you get varies from 30 to 80%. Now, what precisely decides that, whether it's going to be 30 or 80, which is quite a difference, and financially, so it's kind of something profitable to push, or at least potentially profitable to push oil through long pipelines, helping the fluid to flow with the help of polymers. So you really care about this difference because it's kind of it's translated directly into into profits. So people want to study that, and you also care about it simply because you want to achieve high velocities of submarines or something else. So as I told you, polymers help also in that. So if submarine wants to accelerate fast, one of the ways to do it is it ejects polymers in the flow, in the fluid around it, and then accelerates, and it's getting much faster because of drag reduction. So drag reduction is the main reason why we study the dilute polymer solutions. At least this has been the main reason so far. And if you have polymers which are in this range, so you take their concentration in the chord so that the back reaction starts in this range. then I believe that you will be able to see maximal drag reduction, not in the sense as you will see also this term in the literature. I will not explain it here. However, you will be able really to see maximal drag reduction in the sense what maximum of what you can achieve with polymers. And hopefully, from the study of that problem, you will also be able to make some measurements of polymer distribution in space. And these measurements will actually be much more transparent than when you have a length which is finite. And the interpretation of polymer distribution and the polymer size distribution in the flow is much less immediate. So I think that there is a lot of reasons why you would want to do it in the lab. We can continue that by email. I told you more or less the same thing I told you previously with some variations. So the main reason is that you can both maximize the drag reduction and maybe understand mechanisms of drag reduction. So this is the reason which I didn't stress enough. So let me explain this. So people don't know. So what you know about elastic turbulence, oh, sorry, not elastic turbulence. Elastic turbulence is a term which somehow reserved for something else. So let us call it high Reynolds number, high Reynolds number elastic turbulence, which would be kind of, so you'll see today what's the term reserved for elastic turbulence. In this case, what you have usually in, so here there's a big difference between spatially uniform homogeneous turbulence, which we were considering so far, and actual flow near boundaries, which is influenced by the boundary, because drag is a boundary effect. So drag is more or less means the stress which is exerted on the boundary, and you do need to know how the flow interacts with the boundary, and that creates some significant difference. So what we have in the case of homogeneous turbulence, so homogeneous turbulence is the case which is understood more than anything else. And this is the situation where actually you can understand the system from the viewpoint of cascade of energy. So cascade of energy, as we learned, it starts with some large scale velocity, which lives on scale, which has eddy size L. So eddy means that we have some pulsation of turbulence, which is introduced by external forcing, and we consider how it evolves in time. It starts fracturing, so it starts producing this range L/2, L/4, and so forth. And then you want, we have some fluctuations here in the number of participants, which I can hardly understand. Okay, so when this fracturing happens, the time scale which is associated with eddies at scale n behaves as L over delta V at scale n, with velocity difference at scale n. And if we use simple Kolmogorov estimate, which is okay if Reynolds number is not too high. So at high Reynolds numbers, we need to include intermittency necessarily in these estimates. So if you use this Kolmogorov theory estimate, so epsilon is this average energy dissipation rate, then you have that this behaves as n to power 2/3 over average dissipation to power 1/3. And this is the law which tells you that, of course, the smaller huge troubles with internet. Okay, one moment. So is it huge troubles with internet on your side or on my side?
I see no problem here.
I see no problem either.
Yeah.
Ah, okay. So, all right. So we have this. I'll switch to speaker view so that I can see what you see, hopefully. All right. So we have turbulence which accelerates as you produce smaller eddies. So if you start with large-scale eddies, the typical situation is that time scale of large-scale eddies is much larger than tau. So what it means is that if you wish, you can consider it in terms of velocity gradient associated with scale L, which would be delta V at scale L divided by L, which is, of course, the same as 1 over tau L. So velocity gradient and time scale are inversely proportional, velocity gradient at given scale. So you find that tau grad V at scale L is much less than 1. This is the usual situation. And what it means is that the stretching by large-scale eddies, stretching of polymers, which does exist, so you can think of stretching of small polymers in terms of superposition of stretchings by different size eddies. So the contribution of stretching of polymers by large-scale eddies is negligible. So from this viewpoint, it's kind of there, so to say, Lyapunov exponent is in the range where polymers would be coiled, okay? So large-scale eddies do not stretch polymers. Of course, you can create turbulence where they would, and it can be interesting, but I'm speaking of the usual situation, which is realized in experiments. Again, this would be a direction of research to see what happens when it's not like that. I believe there are some efforts in that directions, but certainly there's a lot of work to do. So then you kind of consider what happens as how the interaction with other eddies happens. So we consider the stretching as superposition. And you realize that there is a special scale, which we call R star, so that time scale of eddies with spatial scale R star is of order tau. Now, this is something which tells you that eddies at this scale already interact with polymers. They will start stretching them, polymers will start contracting, and there will be some interacting state. Now, remarkably, it also tells you that you cannot go, in some sense, cascade is stopped at this scale. This is a prediction which so far was not completely checked. So there are some predictions of this theory with this system, which does assume this. Some measurements were done. So definitely this system captures certain physics, and I'll tell you about that physics. However, the most remarkable, in my view, prediction is that cascade is stopped at scale R star. The reason is that if you continue, if you would think about further decrease of scale of cascade, it would produce eddies which time scale is much smaller than tau. So I consider here limit of small viscosity. So we don't have interference between viscosity and elasticity effects. So if you consider, if you are well above the transition, so that this scale R star is going to be much larger than the viscous scale, that you can verify. So you find the situation that further decrease of scale would produce time scales of eddies much smaller than tau, which is equivalent to statement that it would produce gradients of the flow much larger than tau. And gradients of the flow much larger than tau would not be steady state, because polymers would stretch indefinitely, and this is by definition not back reaction. In fact, you can make some kind of considerations which show to you that this is necessarily so. So in the steady state, you must have finite B, okay? So you consider this equation, and you realize that the solution of this equation is that magnetic field evaluated at the trajectory of the fluid particle, we use the same notations as previously, is given by exponential minus t over tau the same Jacobi matrix as we had previously, which acts on B at time 0 at point X. So this is implicit solution of the equation on field B. This is quite in contrast with magnetohydrodynamics, where you cannot write anything of that sort. I mean, you can formally solve the equation in terms of Green's function, but you don't have any simple equation in terms of, so you can treat this equation formally as linear equation and solve it with the help of Green's function, which is usual way of solving linear equations. However, in magnetohydrodynamics, you will not find anything of that simplicity. So this is the solution, and this solution involves matrix W, which knows about interaction of polymers with turbulence. So it's not W, which we would have in Newtonian fluid, it's a different W. So we don't know what its properties are statistically, up to these general properties which we discussed. So large deviation function, Lyapunov exponent, everything would be different, would be influenced by polymers. However, we know that there is this type of matrix. So then if you take this solution, in the usual way, you can consider the Lyapunov exponent. And here there is a delicate point which I don't want to discuss, but okay, let me discuss it. So we're already speaking with, so why not? So you consider in the same way logarithm of b t q t x over b at time 0 at point x, and this is the limit which you can call lambda 1. So there is, however, a delicate difference here. So you might be wrong. So in this, so this flow V has definitely Lyapunov exponent, which you can measure, and that Lyapunov exponent will be lambda 1. Okay. So then, is it obvious that this field, which evolves in the same way as infinitesimal line element, will be governed by the same lambda 1? Now, I think that you must have questions about what I'm telling, so please ask them. So what I'm telling is this: for this flow V, whatever it is, we don't care what determines it. One of the main things about our considerations was universality. You do not care about the origin of the velocity field. Whatever it is, you can define things such as the first Lyapunov exponent. So in this sense, well, I think that I need to write it because probably you will not ask it for many reasons. So I will write it. So this point is not trivial, and it might be wrong in our paper. So usually our papers are okay. However, this is a delicate point. It took me a long time to understand what can go wrong. So let me explain this point. It's not a big mistake, but it's a bit of a mistake. And it's not obvious yet that it is a mistake. So I'm simply telling you that it might go wrong, okay? So usual definition of Lyapunov exponent, which you would do, is logarithm of modulus of W n. Here, of course, lambda 1 minus 1 over tau. So logarithm of W n. Well, in this formulation, nothing else, because this is dimensionless already. So it's simply this. There is nothing wrong about it, okay? So you can define first Lyapunov exponent of turbulence in dilute polymer solutions. This was not completely measured yet, which is why I'm telling that I might still our paper on that can be okay. It would be good again if some of you would do the measurements of this lambda 1. It's not that difficult. It can be done today. Certainly we have the capacities of computers which allow that. And to measure lambda 1 means to study how it depends on on tau, or this Weissenberg number which we defined, which I remind you is square root of average epsilon over nu times tau, which you might wish. Okay, my computer now does something strange. Okay, so a moment. Yes, okay. All right, so you might define that number in this way. So to measure lambda 1 as a function of this number would be highly interesting and hopefully illuminating, because when you consider interaction of turbulence with polymers, it is small scale phenomenon, okay, in homogeneous turbulence, okay. So we do not see any, so turbulence at large scales would be, at least theoretically, which means that when you have good separation between different ranges, as the theory assumes, large-scale turbulence is not influenced by polymers at all. So this assumes that this large scale of turbulence is much larger than this R star, okay? So if this is so, it means that cascade of energy proceeds without interacting with polymers for quite large number of steps of cascade, and eventually it comes to interact with polymers. So please think of it, because again, it might go wrong, because in turbulence we have structures of vastly different scales. So all these cascade type arguments, they assume that you can consider cascade of energy in terms of eddies, and eddies are fluctuations of turbulence with certain characteristic scale. Now, if you have fluctuations which have vastly different scales, then there is simply no unique scale of the given structure of turbulence, or pulsation or fluctuation of turbulence, and then things can go wrong. So everything what I'm telling you is something which kind of you need to understand as a kind of phenomenological approach, and phenomenological approach can go wrong. All right, so this would be definition of lambda 1. Hopefully somebody will ever measure this. There is no reason why not. Besides fashion, today people concentrate more on elastic turbulence, of which we speak later. However, nothing, well, changed. We don't understand drag reduction in high Reynolds number turbulence, which is relevant for pushing fluids like oil through pipeline, and this quantity still remains interesting. Okay, so please do not necessarily go after fashion in your studies. Okay, unless your position depends on that, of course. All right, so this is the definition of the first Lyapunov exponent, which you can do in these flows without any problem. And then if you look at this, you see it's very similar. So this is the solution. So if you consider it in this way, what do you find? You find, well, there is this -1 over tau. Okay, it's there. No problem with that. It's simply some contribution, additive contribution to this thing, and then plus limit as time goes to infinity of 1 over t logarithm w, which multiplies unit vector at time 0. And here comes the possible catch. So at first look, it looks completely the same. All vectors must be the same. So this is going to, so nothing depends here on orientation in the limit of infinite time. For any orientation besides orientation which has 0 measure on unit sphere, you have this limit. So this must be lambda 1. And here is the catch. So we are not completely certain that interaction of polymers with turbulence does not bring B precisely to that special direction for which this is wrong. Okay, or this. So with you, we already did this. We saw how we quantify these vectors n for which this is not lambda 1. So we saw that this is true if this matrix n times initial orientation, if first component of this vector, so this is a vector, its first component is not 0, then the limit is lambda 1. So we have very good understanding at this point at least in principle, you have it all described. You hopefully understood something, and you can always watch it again if you have patience, and I hope that you do, at least if you need. So this is our quantification when this limit is actually λ1. So this is true for all vectors besides those special vectors for which this would be 0, and this defines kind of a curve on the unit sphere of directions of n for which this is wrong. Okay, so here's the problem which can happen, and it does happen, and I'll give you an example because it's an example which, as fluid dynamicist, I think you need to know, that interaction can actually change things in a profound way, that the interacting field can set itself precisely settle in configuration which has, so to say, 0 volume. Okay, and this happens often. So I'll explain it. So you have this limit. However, nobody guarantees that here you can assume that n times, so b unit vector at 0 is of course defined as b at 0 divided by modulus of b at 0, as I guess you understood. So n of b0 can have, it can be, okay? It can be that the interaction between B and V fields will make B precisely to point into this direction, which is kind of doesn't have any projection on, so its projection on this vector. So you rotate it and project it on unit direction, so that projection can be 0. So to decide this, you need to make measurements, and it can be like that, it can be not. And I'll give you an example where we certainly know that it's not true. It's a well-known example, which you do need to study at a certain point. And I think it's significant that you learn this because it has something to do with this system as well. So are there any questions? Remarks? Okay, so let me give you, so we want to understand how polymers interact with turbulence, and we can be guided by some things which we already understand from the similar system of magnetohydrodynamics, which you will often hear called as MHD. So you take the usual equations of the Navier storms. So dTV plus V grad V equals minus grad P plus nu Laplacian V. And divergence of V is 0, and I think it's hardly visible, this color. Yes. Okay, so let me see if this will work. So you consider the curl. This is also not good. Okay. So you consider the curl, which is our usual definition of vorticity. And you know very well that vorticity obeys the equation that dt omega plus V grad omega equals omega grad V plus nu Laplacian of omega. Okay. Now let us compare this with, let us look at it in the case of magnetohydrodynamics. So in the case of magnetohydrodynamics, we would want to consider a special case, which is, so you have the magnetohydrodynamic term, which is B grad B. Okay, and of course it's good that you have both systems on the board, you can compare them. And the magnetic field, of course, incompressibility, so the ideality condition doesn't change. Magnetic field obeys the equation that dTB plus V grad B equals B grad V. And we will take special case where magnetic diffusivity actually equals to the kinematic viscosity of the fluid. So we'll take the case where magnetic diffusivity term is nu Laplacian of B. Well, it's not something special. It in fact can be realized. You can have a situation in the laboratory with no problem where magnetic diffusivity and kinematic viscosity are identical coefficients. It's not something imaginary. It can happen. So for this system, you can kind of derive this type of equation if the same equation for vorticity holds, provided you consider the situation where magnetic field actually is so small that you can neglect this term, which is proportional to B squared. So if the amplitude of magnetic field is small, you can neglect this. Okay. So you can consider this system of equations. Magnetic field in this case is passive. It is simply transported and stretched by turbulence. And you understand, in fact, how it happens. Without this term, we learned this equation, what it means. So without the magnetic diffusivity term, it's simply stretching of magnetic field lines. And with this term, okay, there's some diffusion, but you also understand quite well, hopefully, the Laplacian term. So that's not a big problem. For some reason, this color is blurred, so I will not use it. Okay. So what we know about this system? So we know that still vorticity obeys this equation. And now you see a remarkable thing, which is was observed by Batchelor, that magnetic field and vorticity obey completely the same first order in time equation. So, well, this looks quite striking. Does it mean that they have the same properties? And of course, that was the beginning of the story, that people wanted to understand if the things which obey the same equation, which is first order in time, have the same behavior. Now, it could look to you that, well, of course they must, because if you start with the same initial condition, well, you know the system, the theorem of uniqueness of solutions of first order in time equations. So if the initial conditions for B and W are the same, then the solutions will be the same at all times. So it looks like we could have completely identical solutions. Moreover, there's no problem to do it like this. So you can tell that, well, maybe W is some special field and B is not, so maybe you cannot take it, but yes, you can. So the only thing which you need to do, you take some initial condition. So you have some initial condition for W at time 0, which is simply whatever vorticity is at time 0. And you take as initial condition for B at time 0, some epsilon times W at time 0. Okay? There's no problem whatsoever. Take this epsilon so small that you can neglect this term. Everything is self-consistent. Nothing does not let you to take B as given by the same initial condition as vorticity. So the system of uniqueness of solutions implies then that because B is simply multiplicative in this epsilon, the solution at time t will be epsilon times W at time t. So our result is that we have that because vorticity in stationary turbulence is a stationary field, then also B must be a stationary field. It must always remain small. Please tell me if you can see the board here, because I see it blurred somewhat. Is it visible? Please, somebody tell me.
It's okay. Yeah, we can see it.
Okay, so I told that
I don't know if the record will capture it because it has lower quality, but we can read it now.
Okay, so if you can read it now, I presume the record, I think it's the same, isn't it? Well, okay, never mind. So here it's understanding which is important. So there's nothing which, so it looks like it must be the same, okay? However, there is a catch. the catch is that we do know that B in fact grows exponentially according to the system, and it's certainly not stationary. So what goes wrong? What goes wrong is the usual thing in fluid mechanics, that not every solution is actually realized. And we need not only that to speak of some solution which is physically realizable, we need to guarantee that it both solves the equations and it is also stable. So if it's not stable, then we are kind of, we have a problem, and this is no longer a good solution. It will simply never be observed, okay? Or you can observe its instability, but you will never observe it realized for some finite time. So then you ask yourselves if this solution, so how you understand it. Say you do the simulations with this system, you start with the same initial conditions, and in principle, if you have numerical errors which accumulate and you do not impose that the numerical errors are completely the same, so if you don't impose this, you will see that the solutions will diverge. And the reason is this, that magnetic field, when you the flow doesn't care where magnetic field is pointing. It doesn't care about its value, because in this formulation, the flow is completely independent of magnetic field. So the orientation of vorticity must be such that it will not grow in time. It will remain stationary, okay? So in the limit of infinite time of evolution, vorticity was of certain typical value, and it remains of the same typical value in the steady state. So this is realized by very non-trivial correlations between direction of vorticity and this directions of stretching of which we spoke. And people do study that. You can look at works by Mennevo and some other people who studied these things. So you realize that vorticity does not point in any sense arbitrary direction in space. It points in the direction of space which knows about stretching directions. In contrast, magnetic field can be whatever. So if there is some small fluctuation in direction of magnetic field, after a while, it really, the initial very special orientation which we gave it according to this initial condition will simply get forgotten, and magnetic field will evolve as a typical vector in this velocity field. So the difference, of course, is that the flow does not care about magnetic field, but it does care about vorticity. Vorticity, in a trivial way, has back reaction on the flow, because simply curl of the flow is this vorticity field. Okay, so this gives you the idea that when things are coupled, it can be that behavior of coupled fields is simply non-generic, because they interact with the flow itself, and then their transport by the flow is non-generic. So this is the same issue which can arise here. It was not considered so far. It's somewhat well, it's a bit difficult to communicate ideas to explain what you need to measure. So things take time, and well, there are all sorts of reasons why it was not measured so far. I would be glad if anybody of you would want to co-work on that, because the reason is simple. So people do observe this λ1 in experiments. It seems that they get, so if this is true, if this is λ1, okay, then stationarity means that, so stationarity would tell you that λ1 is 1 over tau. So this would be strict rigorous condition, okay? This is what we wrote in our papers. At that time, we kind of thought that there would be no, well, okay, so it doesn't really matter today what we thought then. We thought it would be true, and this is the prediction which we did. And in fact, in simulations, it's observed that it's Well, it's roughly true, but not completely true. And there was no conclusive measurement as far as I know. However, it is observed that in fact λ1 is of order 1 over tau. So you cannot get λ1 in polymer solutions, which is much larger than 1 over tau. However, what it is and where this B points, it's an open question, and it's quite similar to these questions which are asked by a group by Menevo at Johns Hopkins University about correlations of directions of vorticity and stretching directions. It's the same thing here. What are actual correlations between the directions of B field and the typical kind of stretching directions? Okay, so it would be good if somebody would study it, because it would really bring us insight into this interaction. So, however, with this reservation that it might be not completely true, this is still true. Okay, so it means that, however, so let me to stress this point, let me consider the usual Newtonian fluid. So in the Newtonian fluid, you have the estimate that λ1 is 0.114, and then times square root of average epsilon over nu. And as we discussed many times already, you do not really care about dependence of on the Reynolds number, because it's very weak. So if you look at this formula, it tells you this: if you pump more energy into turbulence, so you increase this epsilon, λ1 increases. Not so the case if polymers are inside the flow. You pump more energy, however, gradients or λ1 cannot increase, so the energy must dissipate by another way, and that way is actually elastic dissipation of energy, as we will consider in a moment. So this prediction seems to be true. It seems to be true, therefore, that the cascade stops at scale R star, and it cannot generate smaller scales because they would produce gradients which would not be in equilibrium, in dynamical equilibrium with elastic degrees of freedom. So if gradients are very large, it would mean that you can simply forget this term, and then you immediately run into problems with, well, it's not immediate that you run, but you do run into some problems with energy conservation and so forth. So you need to have this balance between this and this term, and that means that gradients must be in the interacting state. They must be of order 1 over tau. All right, so let us look at the energy conservation in these systems. David, I think you are leaving soon, so if you have any questions about polymers, please ask. David? Okay, maybe already left. Okay, so I had a request to speak of polymers before 11 Spanish time. I guess we have at this point the same time as in St. Petersburg. We had our clock moved today. So if there are no questions, then we go to the energy considerations for this system. Please think of this example about vorticity and magnetic field. It gives you actually quite a good idea of the non-trivial effects of interaction and what interaction can do on the level of Lagrangian terms. Right, so we consider this system, and we realize that without simply by analogy with magnetic field, with magnetohydrodynamics, you realize that if nu equals 0 and tau equals infinity, the system is conservative, and it has the energy integral up to singularities, which is simply sum of kinetic and magnetic energies. Okay. Now, when I tell up to singularities, it means this, that if you have, without these terms, without dissipative terms, if you have a solution which is smooth, then certainly it conserves the energy, and then there's no problem. However, it could be that solutions, in fact, can develop singularities, and that development of singularities would mean that there is effective dissipation there. As you know, for instance, in compressible turbulence or compressible flows, you can work with solutions with equations which don't contain dissipative coefficients, and yet you would have discontinuities in the flow which would effectively produce dissipation. So this is that remark. We will not consider these possibilities, so we will assume that the system is conservative, and then we consider how energy changes in time, and of course energy is not a vector, so dE dt. So then it's kind of easy to see that so okay, let me write this down. So you have the usual terms. So when you take time derivative of v square, you have minus integral vi v grad vi, and then you have plus v grad p. Then you have minus nu vi Laplacian vi. So these are the usual terms of the Navier-Stokes equations. And then you have a new term, which is plus integral vi, here please index I, b grad bi dx. So this whole thing is d dt of v square over 2. Then there is similar term which comes from derivative of magnetic field. So here you need to multiply with bi. So we find minus integral. Here you have bi v grad. So let me here not take minus outside. So minus bi v grad bi. Then you have the term which is plus bi b grad vi. And finally, you have the term which is minus integral of b square over 2 dx. Okay, so this whole thing is time derivative of b square. Okay. All right. So then you look at these equations and you realize that some of the terms here give 0 because they simply correspond to fluxes of energy. So for instance, this term you can write as usual, you can write it as, so one of the things which I want to tell you is that in magnetohydrodynamics, people often use the analogy with kind of magnetic field as kind of inner elasticity of the fluid. And these equations gave actually this analogy some very concrete meaning, showing that actually elasticity is describable by the equations which are very similar to magnetohydrodynamics. So if you consider, for instance, this term, it is equal to integral of v grad v square over 2, which due to incompressibility you can write as divergence of v square over 2 dx, which is then 0. We assume that the integral of full derivative is 0. Similar thing you can do with this term, which would be integral of divergence of v times e dx. So this is also. Now this term we integrate by parts in the usual way. Now this term, which is what I wanted to show you, actually is, you can see that it's very similar to this term. And in fact, they combine into full derivative because you have the identity that vi b grad bi, which is the amount of energy which is transferred per unit time from inertial degrees of freedom into elastic degrees of freedom. And then you sum it with integral bi b grad vi. And you find that you can write it as integral of b grad dot product of b dot v dx, which in turn is integral of divergence of b times b dot v, because magnetic field, well, not b is solenoidal field after transients. So again, we find integral of full derivative, and this is here. So the energy which is transferred to elastic degrees of freedom is released via this term. So in the absence of, and also this term can be written as full derivative. Again, you can write it as v grad b square over 2, this term, without minus, and this can be written again as full derivative because velocity field is incompressible. So all the terms disappear besides the viscous term, and we find that this is equal to minus nu integral grad v square dx, our usual term in Navier-Stokes equations, minus integral b square over tau dx. So these are the equations of energy changes in the coupled flow of elastic and inertial degrees of freedom. It shows to you something remarkable, that because grad v square, so let me consider it as local equation. So on average, energy dissipation. So this is change of energy due to the interactions and dissipation of these terms. So this must be equal in the steady state. We must have that average energy injected by forcing, which if you want to introduce explicitly, you introduce here the force. So it's turbulence which we excite and not directly the polymers. And then epsilon is simply average of the force of the power. And according to this equation, this must be equal to nu times average of grad v square plus average of b squared over tau. And this is kind of remarkable because you see that dissipation, if you consider limit which is well above the coil stretch transition, that dissipation is elastic. So let me show this. So at the coil stretch transition, which means that where the B becomes macroscopic degree of freedom, which interacts with the flow, you have that average grad V square is of order of 1 over tau square. Okay, now consider situation now well above the transition, which means when you consider energy which is injected into the flow in the amount which is much larger than nu over tau square. Then you find from these equations that actually, because grad V square, however large the energy the injected energy is, remains of order 1 over tau square, by the condition that B does not get indefinitely stretched, which would violate the condition of that there is interaction. So grad V square must be of order 1 over tau square, and you find that actually all the energy is approximately dissipated by elastic degrees of freedom. Okay, so this is kind of remarkable conclusion, and we will explain it after the break. You will see the reasons for this and the physics behind it. Okay, so please ask me in the chat if you have any remarks. Okay, we continue. Are there any questions you have, remarks? What we talked about, we are studying quite a new system in fluid mechanics, which was introduced a long time ago, and yet there is no definite conclusions on it. So
Itzhak, we cannot see the screen.
Yeah, yes, because I didn't turn on.
Okay, I take this time to, I don't know if I can ask you to repeat before you jump to next section. Let's say you did some conclusions there. The velocity gradient square is proportional to 1 over tau square. Could you repeat those? How do you make those derivations, conclusions?
Yes. So for starters, what you're telling indicates that it's not obvious that I'm kind of giving you consistent exposition, because you tell that I jump to the next thing. So I don't want that you have after this course the impression that it was kind of jumping from one thing to another. So maybe it's good time to review what we did, and then I will turn to this asymptotic quality, how you see it. So in this course, we studied very consistently, in my view, the foundations of Lagrangian chaos in turbulent flows. So these depend on the intermittency of turbulence. So we studied turbulence of gradients of turbulence, which is properties of gradients, which determine the evolution below the scale of smoothness of the flow. We discussed with you the problems in resolution, that viscous scale is a strongly fluctuating quantity in high Reynolds number flows. And then we had a discussion of dissipation. Now, I immediately, I want to make a remark, which I didn't do when we made this exposition. So one of the main characteristics of intermittency is the exponents of dissipation field. So let me call it gamma tilde of k. Oh, well, sigma of k. So we did not speak about this. However, so I remind you that epsilon tilde is simply nu grad v square over average dissipation. So it's the field which dissipates in the turbulent of local dissipation of energy due to viscosity. And this is the field which, as we discussed, not in detail, but discussed, that this is a field which becomes multifractal in the limit of infinite Reynolds numbers. At finite Reynolds numbers, the multifractality can be characterized by the exponents sigma of k, which give you the dependence of moments of this dissipation, fluctuating dissipation field on the Reynolds number. Now, and an example which I gave you was, say, that in clouds you have epsilon, which changes by orders of magnitude if you have some linear probe, and you simply see that it has very strong fluctuations. So what I did not tell you, and I want that you learn from this course, is that in fact this sigma of k with a very good approximation is an extremely simple function. And this was noticed, well, it was observed in the paper with Lee, which I sent to you. So it's kind of, it gives you the shortest route to all anomalous exponents of turbulence, which is why I want to tell you this. So sigma of k in general is similarly to this function gamma of k. It is a convex function, which is 0 at 1 by definition, 0 at 0 by definition. So in general, it has this type of form. quite similar to gamma of k. Now, what we observed is that actual data is completely consistent with simple parabolic approximation for this function. So this is something like minus 0.1 k 1 minus times k times 1 minus k. Okay, or you can write it as 0.1 k minus 1. So this is the simplest function, which is convex and has two zeros at 0 and 1. There's nothing simpler which you can write. It's quadratic, and then the only free parameter is this 0.1. Now, the reason why this log normal approximation works very well, and it is different from log normal approximations which you'll find in books, which describe coarse grain dissipation and not the full dissipation. So this does work, okay? It describes all numbers not worse than any of the feats of exponents which were done so far. And the most relevant thing is that if you use the relation between exponents of turbulent flow, which determine you the scalings of moments, this r to power zeta of k. So I remind you that velocity differences scale as r to some non-trivial power. If you find this zeta of k by the formula of multifractal model, from this sigma of k, there is unique relation between them. They're not independent. You find that this zeta of k, which you find from this zeta of sigma of k, it's a simple calculation, fits completely all the data. So I'm not telling that this is true for all case. It's a local approximation, which is true only for not very large case. However, I want you to know that there is a simple way to derive all exponents of turbulence which characterize intermittency from these considerations, okay? So this is something to remember, and I want you to remember it because it was an observation which came out only recently. For reasons which are mostly historical, people never really concentrated on this field. They always considered coarse grain dissipation. And again, the reasons are that it was coarse-grained dissipation, which was available in simulations, and only recently we started to resolve well the Kolmogorov scale, the viscous scale. Again, it's not completely understandable why it was not observed before. It is like that. So we studied dissipation. You have this remark on calculation. So dissipation and intermittency mean that the exponents are anomalous, and you can anticipate large fluctuations in different properties, which are gradients of turbulent flow, viscous scale or dissipation scale, not Kolmogorov scale. It's only kind of average value is Kolmogorov, but it's not even average. So it's Kolmogorov scale is something which is very well, it's simply kind of, you use only energy dissipation and you get this average, but the scale, but it's not reflecting so simply any of the properties of this fluctuating viscous scale, only if you neglect dependence on it, if you neglect intermittency. So we need to know intermittency when we study Lagrangian chaos, because Lagrangian chaos, as it has become obvious only very recently, depends strongly on Reynolds number. So when you speak Lagrangian chaos in turbulence, it's immediately the sign that you need to think about very unusual type of chaos from viewpoint of dynamical system, which is enhanced by a large parameter. So everything is strongly fluctuating, and you can consider Reynolds numbers which are not very large and disregard this, but as soon as you move to applications which involve high Reynolds number, and there are many of them, you really need to think about this dependence on Reynolds number. And I stress this thing because there is plenty of measurements which are to be done in coming years, and I hope that some of you will do them. So this was not consistently studied yet, okay? So we studied then Lagrangian chaos from the very beginning, essentially to very end. So we introduced, not in chronological order, but we introduced Lyapunov exponents, then their finite time versions, then generalized Lyapunov exponent, and then the relation between statistics of finite time Lyapunov exponents and generalized Lyapunov exponent. And we considered applications of these quantities, by far not all of them, this huge list of applications. So I'm not, you do not have lectures on something which is kind of academic interest. It's really very applied field. And we talk as applications about polymers and turbulence and about magnetic field. I wanted to speak more about also inertial particles. I might have in the end some remark on that. However, it might look to you ironic, but we did not have time for that. And the reason is that this course really establishes everything from the very beginning to the very end. So wherever I could, I spoke about how you do simulations with that, what is the procedure, and where the problems can be. So I hope that after this course, you will be actually well equipped with dealing with real problems, and with the help of maybe some literature, you will be able, so you have quite a number of problems which are open, which I think would raise interest, and I described in this course. So I think that you can cope with these problems with maybe some help from, certainly with some help from literature. However, there's nothing at this point which I think would prevent you from doing research in this area, should you get interested in this. So then we are considering new type of problems which arise when turbulence actually excites new macroscopic degree of freedom, which is elasticity. So we have kind of potential inside the fluid that there are dissolved polymers inside it. They are, if turbulence is not very strong in the sense of mean energy dissipation, these polymers are in coil state, so it's only potential. They don't influence, they are not observable macroscopically. You would look at the dilute solution of polymers, you will see that it behaves more or less as the usual fluid. However, when it passes certain threshold, it excites this degrees of freedom unfold, and you start having a new type of flow, new type of turbulent flow, and we are only talking about some properties of that flow. It's still, again, an open area of research. So, and we discussed new type of, sometimes it's called, so considered a different type of non-equilibrium phase transition, and this type of transitions are called, where actually the transition is caused not by increase of epsilon, but by increase of Reynolds number at fixed epsilon. So this is kind of inherently transition due to intermittency. And I think that in some sense you had a very detailed exposition of many things. And I do not see much holes in in the material on Lagrangian chaos which you had, which usually is not the case in typical courses which I myself deliver or others deliver, because you simply cannot discuss all details of everything in the usual situation. So I hope that this will not look to you as really kind of jumping from something to something. It's really, I was coherently moving in certain direction, and I hope that we arrived somewhere. So regarding, so this is the end of this short resume of the course. Then how you derive this, how you understand that grad v square must be estimated as 1 over tau square. So the reason is this, that grad v square cannot be much larger than 1 over tau. Because if it's much larger than 1 over tau, it means that this term is negligible, and b is simply extending infinitely. And you cannot allow infinite extension of b, because then the equations will not be consistent. You will have here infinity with nothing to balance, okay? So you must have that gradients of v are of order 1 over tau. Simply cannot have anything else. Gradients of v also cannot be much smaller than 1 over tau, because if they were much smaller than 1 over tau, then this term would be negligible, b will disappear, and turbulence would return to the state of Newtonian flow, And by our assumption, Newtonian flow has the property that it would stretch the polymers. So this would also be inconsistent. So the only possibility is that grad V square is of order 1 over tau square. Is this explanation understandable?
Yeah, thank you.
Okay.
Let me tell you that I also never thought this was jumping between topics. Is the word I used because you said you were going to speak about some other more detailed topic, but I never thought this was jumping from.
This is okay. It actually hinted me that I need to make an effort to review the course for you, so that you can see what we were doing. It may look to you as a bit because, well, it may look to you as not completely coherent or consistent. In fact, I made an effort to make it a very concentrated course on something very concrete, and I hope that at least for some of you it worked. So this is then this grad V square, which you estimate in this way, and then you come to understanding that if you put so much energy into turbulence that average, so the work which you put in per unit time per unit volume is much larger than nu over tau square, then you are in a state where energy actually is dissipated by elastic degrees of freedom. So you can actually understand this quite in detail qualitatively and also quantitatively. So the what happens is this, that you have this cascade of energy. So we assume that epsilon is much larger than this. However, at large scales, you assume that still turbulence does not excite polymers, which means that when you consider typical velocity gradient associated with large scales, which is epsilon n to power 1 over 3, average epsilon, Kolmogorov estimate divided by L. Now, at large scales, you can with no problem use Kolmogorov type estimates because you are not deep inside the inertial range, so there is no cascade which developed, and then there is never much intermittency at large scales. At large scales, statistics of turbulence is not so much different from Gaussian. It could in fact be Gaussian if you made some special effort, but it's typically kind of order of 1 fluctuations, something, okay? Which is of course dependent on what the force is. So, so at large scale, turbulence is not universal. At small scale, it is. So then we assume that this quantity is much smaller than 1 over tau, which means that polymers are not stretched by large scale eddies. What that means is that cascade starts at scale L as in Newtonian fluid turbulence. Okay, so this is quite a significant conclusion. And again, it was not completely conclusively confirmed. So there are results which confirm this. There are results which don't confirm this. And in a moment, I'll tell you about a good technique for numerical simulations of this system. Maybe, well, since I already, well, then it would be jumping if I do this. Okay, so this conclusion is kind of true as long as you can be certain that there is no kind of inverse cascade from the scale R star where polymers start to interact with turbulence. So it could happen. It could happen via geometry. It could happen via other mechanisms. So the results in literature are in both directions, that there's this influence at large scales, there is no influence at large scales. So it depends very much on Reynolds, and it's again something which is still open to discussion. So then you have that, assuming that this is true, so from, at least from theoretical viewpoint, it seems to be okay, that it's not obvious why it should not be true. So consider it as kind of phenomenology of turbulence in this case. And phenomenology is always kind of thing which can be changed if we encounter that some things are wrong. So, okay, let me erase this. And then, so let's have this picture of the cascade. So the cascade proceeds as we saw. So it starts at scale L, it goes to smaller scale, and so forth. So this evolution of these eddies, and eventually it reaches the scale R star, where local dissipation, local time of eddies, which is T of R star, which according to Kolmogorov's theory is R star to power 2/3 divided by epsilon average to power 1/3, is of order tau. Tau. So when you reach this scale, which you can get from this, that R star is something which is, okay, I designated with superscript, so let's do that. So R star from this is of order of tau to power 3/2 times square root of average energy dissipation. Now this scale was in fact introduced by Dejean. By completely different considerations, they actually thought at that time that polymers get stretched to this scale. Apparently this does not happen, yet the scale itself is relevant. This is the scale where cascade of turbulence changes, and it changes in a very special way. The velocity gradients cannot continue. So as you consider smaller scales of turbulence, velocity gradients increase. In other words, cascade generates smaller scales and larger gradients. Each subsequent eddy has larger gradient associated with it. And by definition, gradient associated with eddy of scale L is the velocity difference at this scale divided by the scale, okay? So as cascade progresses, you have larger and larger gradients, and then you reach the gradients which are 1/tau, and then polymers tell, stop, you cannot do it anymore, because we cannot be stretched up to infinity. We will resist that, and then cascade cannot produce larger gradients, which means that the flow gradients of V must be constant at scales much smaller than R star. In other words, R star must be correlated, a scale of correlations of gradients of turbulence, or in other words, R star becomes new scale of smoothness of the flow. Okay, so the flow at scales smaller than R star has this property which we used below the viscous scale of turbulence. So this is R grad V, and in fact it is of order R/tau, because grad V is of order 1/tau. So you find that you have quite a different flow, where gradients, in fact, scale of smoothness is R star. And you can wonder where viscosity goes. What does it do in this regime? And viscosity does appear, but it appears at much smaller scales. It already changes what happens when you are in the range of dissipation of energy by elastic mechanisms. So what what you find then is something of this sort, that spectrum of turbulence in dilute polymer solutions must have this type of form. So it starts as Kolmogorov law, k to power -5/3, and we have discussed this small correction. It exists there. Then you have the scale, which is 1/r star. And here, quite unusual range starts, which is still a power law. This power law decays faster. So it's k to power, let's call it -α, where alpha is larger than 3. However, apparently it's not much larger than 3. It's not a usual dissipation range, it's elastic dissipation range. So what happens in this range? Viscosity is negligible. Oh, too much written in the same place. So here, make an effort to use other colors somehow. Let's see. So here, viscosity is negligible. And everything which happens is simply polymers release energy, and the energy is also transferred to smaller scales or larger wave numbers by smooth flow. This is something which we will study in a moment, how this happens. This process is in fact quite simple. And then finally there is a scale which is a new viscosity scale. So it's not the same as Kolmogorov scale. And here energy spectrum decays fast. So here fast decay of the spectrum. So one of the predictions of the theory was that in this range there are actually elastic waves. So you can, in these solutions, there will be elastic waves with characteristic wavelengths which are inside this range. And this prediction was actually confirmed experimentally quite recently. In a bit different setting, however, it's the same physics. And this paper was published in Nature Physics, I think. So they relied on our theory and they were able to observe the waves. So it took quite a lot of time. So this is Nature Physics, I think, 2020. If you want, I'll send you the reference. So these predictions were done quite a long time ago, and only recently they started to get into this range and see some confirmations. So the main reason is that actually resolution of scales in somehow they could not reach the scale R star. And the reason is that you need to solve coupled system of equations for two fields, which increases significantly the number of degrees of freedom. So similarly, there was a problem to reach the scale, both experimentally and numerically. And for some, so this is something which is yet to be done consistently. We still do not have any good measurements of this spectrum. So apparently, well, it's a bit exaggeration. So we have some measurements, but in a bit different situations. Say in this paper, there is a measurement of spectrum. The measurement of these predictions is still to be done. And before we go to the derivation of this new range, which was not existent before, so it's completely characteristic for this interacting system. It doesn't exist in magnetohydrodynamics, so it's a unique property of turbulence in dilute polymer solutions. So I'll do some remarks. So for starters, this is description of homogeneous turbulence in dilute polymer solutions. So I repeat, you start with large scales, you have the usual cascade, the turbulence generates smaller scales and it generates larger gradients unless they reach gradients of order 1 over tau. Then there is already excitation of polymers by these eddies. And wherever there is excitation of polymers, there's also dissipation of elastic energy. So you put energy into stretching, they dissipate energy all the time. So there starts to be dissipation of energy. Do not think that polymers have size R star. They remain much smaller than that. R star is the scale of correlations of their stretchings, okay? So if you would be able to have a look at instantaneously at where polymers are and what their stretching is, you would see that they're actually pointing in the same direction, not over scale, which is Kolmogorov scale, but over this scale R star, okay? So it's completely different physics. You will see different things. You will see different scale of smoothness. You see different spectrum. So this is kind of something which is yet to be studied. And this is all about homogeneous turbulence. Then in the end, you want to have predictions for drag reduction in turbulent pipe flow. And this becomes really difficult because you need to understand how the structure, which more or less holds in the bulk, far from the boundaries, how it it is matched by the flow near the boundaries. And this is, there is some insight from the works by Lamley, who did a lot for understanding of turbulence in these solutions. This is, they did not have all the mathematical techniques at the time. However, this person actually came quite close to the modern understanding of many things. So in one of the works, there was a mechanism proposed for how drag reduction happens in pipe flows. This mechanism is not completely correct. It's not in any sense the end of the story. It captures some properties which are seemingly true. And we do need to get more understanding of these things. It's completely, well, not complete, it's absent today. So there's no, to say it plainly, there's no good theory of drag reduction, at least in my view. And no good theory means that it's not simply that you don't have some device in your mind. It means that you cannot control it. So you cannot control drag reduction because you don't really know what happens there. So you don't know where to direct your efforts. So this is open area, and I I cannot fully recommend working on it because many people worked on it. However, if you want a challenge, this is definitely a challenge. So how you can derive these properties? Are there any questions? Okay, I see that there's something in chat. Okay. Can we say that the fact that the flow becomes viscosity independent with the polymers is analogous to the case of turbulence near a rough wall, where once the bumps are high enough, the viscous effects to the mean flow become negligible? Well, this is not completely, well, you know, viscosity, if you consider viscosity, one moment, I need to open the door, one moment, please. So when we say that viscosity is negligible, it's not completely so, because what we actually mean, if I understand what you're talking about, is that there is very narrow viscous layer near the boundaries where viscosity is still relevant, because without viscosity you do not have very significant thing, which is no slip boundary condition. Okay, so viscosity is something which often is only relevant in vanishingly small fraction of the flow. In the limit of zero viscosity, this fraction becomes zero, and yet it rearranges all the flow because effectively it changes the boundary conditions. And boundary conditions then influence all the flow, and this is especially obvious if you consider potential flow, incompressible potential flow, because that flow is determined by solutions of Laplace equations, and solutions of Laplace equations are completely determined by the boundary conditions. So boundary conditions are not a trivial thing. So viscosity does a lot of things, despite that it is small and relevant only in. So when you tell that viscous effects are negligible, you might have in mind that well, dissipation, for instance, the energy which is taken from large scales, probably what you have in mind, is somehow disappears due to these bumps in the end. In some sense, yes, but still you need this no slip boundary condition, I think. So here it's a bit different, because by themselves bumps are not dissipative, okay? The structure of the boundary is not a dissipative thing. Dissipative thing is viscosity. So here we have actual dissipative thing, which is elasticity of turbulence in this tau. So this is actual dissipation. So it's a bit, I think it's still a bit different. So the flow becomes viscosity independent. This is true. In fact, there is very curious possibility, which I'm actually glad that we talk about this, because there is something, it's quite probable. So here, please listen, because it might be, in fact, relevant, quite an interesting direction of research. So it seems quite reasonable that if you erase viscosity, and here I'm not completely certain, but it seems possible that the system has well-defined steady state. Now, if this is true, which maybe it is, then it gives you kind of interesting thing. It gives you a model which is nearly Lagrangian, because the usual problem with passing to Lagrangian frame is that, of course, you have gradient of pressure, but that's not the biggest problem. Laplacian behaves very badly under transformation to Lagrangian frame. So if you don't have that term, this system might have some simplicity. It's very nice, really, kind of. You have very simple physics, and it might even make sense to consider it incompressible case without pressure, because it's also kind of as a model. So it could be that this system is producing steady state, which you can somehow theoretically study and progress in it, where you inject energy into velocity, velocity transfers energy to elastic energy, and then elastic energy dissipates it. So it's kind of very appealing structure in terms of both physics and mathematics, because you don't have the Laplacian term, and it looks a bit nice. So I think that the flow in this case is maybe, if you consider it within the frame where V is actually defined, so you can consider this the flow of Navier-Stokes flow without any boundaries. So you consider it in infinite space with F, which is, if you wish, is stationary process and with specially uniform statistics. So you get solutions which don't, in fact, decrease at infinity, or you can have F, which does decrease at infinity, However, there's no problem to consider these equations without boundaries. So viscosity in that case is probably really negligible because you don't need no slip boundary condition. And then it's kind of, well, I would think that this is, if you want to study what elasticity does, maybe you need to study with this system of equations. Now, returning to your question, with bumps, I think you cannot do anything like that because viscosity is still relevant near these bumps, and by definition, you cannot do without bumps. Now, you might want somehow to simulate bumps with a force. So what if you take a force which kind of does something similar to the flow which bumps do? Maybe. So I think that needs to be studied. So I told you what, so I think that viscosity is still relevant there. It's a bit different thing. However, it might be that there is a way actually to get completely rid of viscosity and think about the flow without it. So I hope that it answered this. All right. So if there are no more questions, then we continue. Let me see how we are with time. Okay. All right. So we consider auxiliary problem, and I want to explain to you the reasons why before we do so. So this is about turbulence in the case of homogeneous turbulence. Well, maybe directly to that. So you see that dissipation is very simple in some sense. It is linear dissipation. The decay is simply, so the decay term is proportional to the magnetic field. So then you consider an auxiliary problem, which is, well, let me erase this for the moment. So the auxiliary problem which we want to consider is passive scalar. So passive scalar field is very simple. Well, to state, not to solve. You consider some field which specifies density of particles which are traces in the turbulent flow. Then if you can neglect the Brownian motion of these particles, then you have this law, and you usually want to have some force which injects fluctuations. So on average, the force is assumed to be 0, and also average of theta is assumed to be 0. So you want to consider only fluctuations. Now, what does that mean? It means this. Say, if you inject dye into a turbulent flow, it's mixed rapidly, or, well, with its rate throughout the whole volume. And in a while, you're going to see completely uniform color holding in the volume. Then, of course, there's nothing to discuss. There are no fluctuations. Then you consider that before this happens, completely uniform field, you inject a little bit more color. So it is also smeared. But if you consider the process where the flow dissipates, smears, makes it uniform, however, external source, which is designated by phi here, constantly injects fluctuations, then you get some steady state, okay? So the force introduces fluctuations, and or simply inhomogeneities. So average of phi is 0 means that you do not introduce particles, you introduce their disbalance in different regions of space. So for instance, you take particles from one region, roughly speaking, and artificially put them in another region. Or you can create it in other words. For instance, you introduce dye color, red color and red dye in some region, and say anti-red, so to say, color in another region, so that some color which if they encounter each other, so this kind of no color at all. So this, of course, is figuratively speaking. So this is what the source does. And then you need to introduce explicit source of dissipation. So this equation will only accumulate fluctuations. So often you introduce here diffusion coefficient, which is you simply introduce d times Laplacian. This is advection diffusion equation which we wrote previously. Or you can consider the situation where there is linear decay, and this is actually the situation which is relevant for understanding polymers. So in this case, you do have a steady state, and this steady state is realized because phi injects fluctuations, and then they are damped linearly by this term. So we want to consider the properties of this steady state, and actually, in this case, the spectrum of passive scalar fluctuations of this field theta does have a power law, which is very similar to this power law which we want to derive for polymers. So this we will do after the break. Unless you have any questions, we will study then this problem. Okay, so we take a break for 15 minutes. We continue. I would like to thank all those who survived until this last hours of the course. So I do encourage that you interrupt me, ask me, because these are indeed last opportunities for speaking about things which you need for your work. So we are continuing to study the interaction of polymers with turbulence. And the problem, which is, if you understand this problem, you can understand the spectra which arise in this situation, is this problem of passive scalar field, which is simply kind of density of fluctuations. So it's theta is deviation from the average level, not the field itself. So theta is not sign definite. It's in fact has a zero space average. And phi is the source of fluctuations, not source of particles. And in the presence of the source of fluctuations and linear damping, you have a certain non-trivial steady state. And what we want to do is to study the properties of this state. So you consider steady state and you solve theta at t point x plus q of tr. So according to this equation, we assume that the source is, so let me maybe start with simply writing the solution and then explain to you what we are doing. So the solution of these equations is this. Theta taken at the in the frame of the fluid particle is simply integral from 0 to t. Well, initial minus the initial value, of course. So this initial value at t equal 0 at point x plus integral from 0 to t phi of t prime q t prime x dt prime and well, I'm doing something not very good because you need to introduce linear damping. So you have here exponential minus t over tau, and here you have exponential of minus t prime over tau. Okay. All right, so this is the solution of these equations. there is a steady state because if you take limit of time going to infinity, this term decays. And at large times, you simply have that here you can, in fact, continue the integration up to minus infinity because it is effectively cut at the scale tau by this exponential decay term. And then the phi must be taken not at initial position. Well, you need to define the trajectory. So instead you take here x, and here you take q of t prime x, which is defined as the trajectory which passes through point x at time t. Okay, so instead you use kind of backward in time Lagrangian trajectories which pass through given final point. So this is the solution. This field is a random variable which is stationary because we assume that the forcing is stationary, has stationary statistics, and we want to describe the evolution which you get in this way. So we assume that the forcing has only large-scale components, large in the sense that we need to define what is large here. There is no inherent scale, so we assume that phi has, for instance, Gaussian statistics. It doesn't really matter. You can use different types of statistics in these problems. Simplest is to take that this is delta of t minus t prime times some function chi of x minus x prime over L, where L is correlation length of forcing. And chi, for instance, you can take exponential of minus x squared. It must be some function which decays over characteristic scale 1. So it can be anything. There's no real restriction which we are going to talk about. We want to consider the situation where R is much, so we want to consider spectrum of this field at wave numbers which are much larger than 1 over L, and also at wave numbers which are much larger than the inverse of viscous scale of turbulence. So the flow is smooth. So R, for R of order of k minus 1, so for corresponding scale, we have that, we assume that Vx plus R minus V of x is R grad V. So we want to consider scales below the scale of smoothness of this field, and also below the scale which is correlation length of the force. So in this case, you do not have any injection of, you can simply neglect the force if you solve things over finite time interval. So what does that mean? So if you take Fourier transform of this equation, you have that it gives you phi of k plus some terms which come from velocity, which you can readily write down. So because we want to consider k which are much larger than 1 over L, there are no significant components of phi in this range. So we can neglect this term. In other words, evolution at these scales simply is, it doesn't have any source. So the field theta, so let me explain this in detail. So if you consider wave numbers which are much larger than the scale of the forcing, then you can wonder where does the field theta come from at those scales. So phi injects theta at scales at certain wave numbers. This term simply dissipates it linearly, doesn't create any new, any Fourier components. So the only term which appears is this V grad theta, which in fact is a term which does produce non-trivial Fourier components. So if phi injects theta with certain scales, then v grad theta will actually produce out of field at that scale, will produce smaller scales. And this is something which is very easy to understand, assuming that this scale L is in fact much smaller than eta, which we will do for simplicity. It fits the problem which we want to consider in the end. So let us make an assumption that L is much smaller than viscous scale of turbulence. In that case, you can actually understand very well what happens, because the forcing phi injects typically some fluctuations of passive scalar with characteristic scale N. Now, this is kind of eddy, okay, in this case, for this problem. And all colors are really not good. So these red colors are gone. And then maybe this will work. Okay, so well, we stick with well, this maybe. Okay, so we'll stick with blue color. So this is the fluctuation which is injected by the forcing. So you can think of it as really kind of some color which is injected. It has some characteristic scale L. Now, because this is statistical injection of this color into the turbulent flow, it does not mean that actually there is certain shape of these regions. This is qualitative description. It means this, that the flow injects some color, which is correlated over scale L. So if you would consider what happens here, it would be something with color which is not correlated. So it would be something like this. Okay. So here there's one color, here is another color, and here is more colors. So the force kind of injects this type of kind of stains of characteristic or blobs of characteristic size L all over the fluid, which are then transported by the turbulent flow and dissipated all the time. They are continuously dissipated in a way which doesn't depend on scale by this linear decay term. Now, of course, we have in mind that elasticity of polymers doesn't depend on scale and has the same linear structure. So what do we do here? We understand that because we made an assumption that N is much smaller than eta, we know what happens with these blobs. So think of them as kind of balls, or in 2D, these are kind of these circles. And then you know what happens. This will be transformed. This is also not so good. It will be transformed into this ellipse. If we consider 2D example, or 3D example, it will be ball transformed into ellipsoid. Okay, so now we simply take a bit different outlook at this process, which we know very well. So what happens when the flow distorts this shape and creates this elongated structure? On the one hand, we get produced large scales. So we started with scale L, and we get this scale, which is roughly L exponent lambda 1t. So we produce large scales. However, at the same time, we are also producing small scales. So this is L to power exponent minus lambda 1t in our 2D example. And as usual, when I write here lambda 1, I simply speak of a finite time Lyapunov exponent, which is typically equal to its value, its limit at infinite time. However, at finite times, this is something which can fluctuate. So what it means in terms of Fourier transform of the field, it means that actually the field gets high wave number components because it starts varying over some small scale. Okay, so in this sense, velocity field, which is large scale field, in this case, eta is much larger than L, so the flow is completely smooth over this scale. makes a cascade of passive scalar from scale L to any scale which is smaller than that scale, or to any wave number which is larger than the inverse of this L. Now, in what sense there is cascade? Because, well, this blob, after some time of evolution, will have this scale. However, the blobs are injected continuously all the time. So there was a blob which was injected later, and say this is at t equals 0, this is at time t, but then there was a blob, say, injected at time t over 2. Okay, so that blob would be, of course, significantly fatter than the other one at time t, and it will have a different wave number, which or different scale, which will be smaller than this L, however smaller by a different amount. So the fact that we constantly inject these blobs of passive scalar means that we produce a whole spectrum of wave numbers, which where wave number is actually determined by the time that has passed since the injection of that blob. Okay, and we want to know the actual spectrum, which you will see. Now, the spectrum, in fact, can be guessed, because you understand that the amount of passive scalar, which we measure by this spectrum. So spectrum is, roughly speaking, the average of squared magnitude of Fourier component of the field up to this volume factor. This is the same thing. So the spectrum, which we will see at scale 2K from this picture, is the same spectrum which was at scale K. So turbulence continuously brings fluctuations from scale K to scales which are larger, including this 2K. So there is some characteristic time during which turbulence brings spectrum from scale 2K, from scale K to 2K. It's the other way around, which I want to think. So, it's okay. So spectrum at scale 2K is spectrum which was at scale at wave number K times the decay which happened because of linear decay during that time. So here we have so-called energy transfer time, T of K, divided by tau. So this T of K is the time which takes the velocity to bring fluctuations, these blobs with smallest size, which is 1 over K, to the scale which is 1 over 2K. Okay? Now, this time, in fact, does not depend on K, because flow is completely, the gradient is uniform. So the time to go from scale L to scale L over 2 certainly doesn't differ from time to go from scale L over 2 to scale L over 4, because the only thing which you need is you rescale this, the flow introduces multiplicative scale. So multiplicative factor to decrease the scale. And in other words, evolution of scales is given by simply this law that this is exponential minus lambda 1t times r at 0. So this is all qualitative considerations, of course. So qualitatively, the scale in this 2D example, the smallest scale of the fluctuation proceeds according to this law. So if you stipulate that r at time tk, well, this wave number, spectrum transfer time, is r at time 0 divided by 2. So this is, if the wave number is increased by a factor of 2, it means that the scale decreased by a factor of 2. So if we stipulate that r at this energy transfer time tk is 1/2 of the initial scale, then it means that from this equality, that exponent of minus lambda tk is simply 1/2. All right? Now, the time which you get in this way does not depend on the initial scale. So depletion of scale is independent of wave number. So tau k is independent of r at time 0. So the only thing which matters is the rescaling factor which we want. So if we want to consider some rescaling factor which is 2, we could use another. Then the time of transfer would be different, but the main thing is the time to go from r0 to r0 over 2 is independent of r0. Please tell me if this point is understood, because that's the main property of linear, well, not the main, one of the main properties of the linear flow. Is it understandable?
I think it is understandable, yes.
Thanks, Emmanuel. All right, I'm asking, well, because I really, well, these are really last hours. There are not many people left. And I have the feeling that this is because you have a lot of material and you cannot follow everything. So this is why I encourage you to interrupt me and ask questions and make this last effort to understand some things. So please do interrupt. Okay. So then this energy transfer time is independent of K. And whatever it is, it's let's designate it by some time, which is so tau Tc. Okay, so this Tc is actually independent of K, and that means that we have a power law solution. That is, the spectrum which must arise at this type of situation is obeys this law, k to power minus alpha. So you can write it as k to power minus alpha times some constant. And you can fix this alpha, so you simply put these answers into this equation. So you consider it as an equation which spectrum must obey. And you find that 2 to power minus alpha must be equal to exponential minus Tc over tau, which allows you to determine what is alpha as, so alpha is this Tc over tau times logarithm of E with basis 2, okay? All right, so this is very simple consideration. It's in fact all the physics of this problem. I hope that you can grasp it. If you did not understand it, it's not something which I want you to think about at home or at other place. Please do ask at this point if you understand this derivation, because it's kind of very kind of qualitative understanding of what is spectrum. It's extremely useful because you need a way to think about what is spectrum. It's also something which you need to think about Kolmogorov spectrum. How does that arise? So this is probably one of the simplest cases where you can actually understand a power law spectrum. So all power law spectra of turbulence in dilute polymer solutions are of this type. Who can ask anything to help everybody else to understand this better? Okay, so then I'll assume that you all understood it. I hope so. All right, so what remains is to put these considerations into a more rigorous mathematical frame, which we will do in a moment. In some sense, I am perplexed because I would think that you need to ask questions here.
I will make one question. I got it. I think I got everything. It's fine.
Okay.
Which is very
Thanks.
interesting. I would have never guessed that this is time independent. This halving of the size. It's very interesting. But I will ask because you said in previous comments also about the forcing, how to introduce forcing, because I'm thinking about simulation. So how sensitive is different source term? In this case, I guess is phi in your equation. How sensitive is all this simulation to this source? How you introduce energy into the system? Is it very sensitive to this energy, to phi?
Okay, so where does this phi enter? And maybe I will make a comment on the numerical simulations of polymer solutions as well. I'll use this opportunity. So for starters, you see that you have here this constant. Now, alpha does not depend at all at forcing phi. You see that alpha is completely determined by the properties of transfer of energy from one scale to another in this range of scales, which is much smaller than the range of scale, the correlation range of the forcing. So alpha is independent of phi. It's completely independent. So phi can be anything. The only thing which we're using is that it does not have appreciable presence at the considered wave numbers. Okay, and this is of course a remarkable conclusion, which also helps you to understand in some sense why in turbulence we believe that similar scaling exponents, say of velocity difference in inertial range, do not depend on forcing. It's kind of the same hope that the transfer of energy is completely local, and you can write so it doesn't know about the forcing. So the energy which is transported from in the same way from K to 2K is, well, transported in some non-trivial way. However, it's completely independent of how we started. And then you can write similar type of equations of stationarity and have a solution which does not know, whose dependence on wave number doesn't know about the forcing. So, however, the forcing is, of course, relevant in order to determine this constant, because this constant, of course, fixes the level of fluctuations, and level of fluctuations of passive scalar is fixed by this phi. So you can understand this in this way. If you plot E of k, then you realize that it starts at 1 over L. So if you have Gaussian forcing where actually Gaussian correlation function where k equals 0 is in fact present, then of course it starts here. But you often in turbulence you want to consider a situation where the forcing is actually present only at wave numbers of certain order 1 over L. And again, sometimes in simulations, instead of having some actual force, you simply fix the value of Fourier component of theta at some k, which is 1 over L. And instead of forcing, you use this kind of boundary condition that there are always present fluctuations at scale 1 over L. So one of the things to do would be, say, to have kind of, for instance, Gaussian fluctuations at scale, at given scale, which you produce with some external constraint. So in the simplest case, you simply write equations in Fourier space, and you tell that certain Fourier components are not decided by the equations, they are decided by the boundary conditions or constraints, okay? So you have in the spectrum the scale 1 over L, and then you have this, well, this is a bit too fast decaying. So then you have this power law, which is Ck minus alpha. Now, the value of this constant C depends on the force. So roughly speaking, energy spectrum at k of order 1 over L is determined by forcing. And it must be given by order of magnitude. You can asymptotically continue the solution up to k, which is 1 over L. So this power law holds only when k is much larger than 1 over L. However, you can usually continue asymptotically to the limit of applicability by order of magnitude, which would give you that this must be of order C L minus alpha, from which you see that C, this constant prefactor in the spectrum, is determined by the conditions at the scale 1 over L. And again, this is very similar to turbulence. So I will use this opportunity to stress that. So for turbulence, you have this law that average of velocity difference to power k behaves as some well, let me write it in the full form. So there is some constant which depends on k. Then there is large scale velocity, and then there is r over L zeta of k. So it's very similar. In turbulence, zeta of k is believed to be independent of the forcing of how you excite turbulence, and for the same reason that you assume that energy transfer in the inertial range is completely independent of where the thing started. So this zeta of k are believed to be independent of force in. We talked about it. I want to reiterate it because in Navier-Stokes equations, we did not talk about this constant ck. These constants do depend on the force, on statistics of the force, and on its values. So a very similar situation holds here, and also for spectrum of turbulence itself. So when you write E of k is constant times k L to power minus 5 over 3. And you can also include the intermittency correction to the spectral exponent. Then the C does depend on the forcing. Okay. All right.
So, but the reason then of this independence is because all the wave numbers bigger, all the wave numbers, they are excited at the same time. Is this kind of the line of thinking? Because I'm not, I follow your words, and
yes,
it feels anti-intuitive for me, like saying that it's independent. I get it as granted, but it's confusing. It's not that it is confusing. It's difficult to believe. It's tough to believe like it's independent of it. How do you get to this conclusion?
Okay, so I'll make well a bit. I'll reformulate the argument. I hope that it will help. So it's not that all wave numbers are excited at the same time. It is that wave number, in fact, they are not excited at the same time. So, however, what happens is that if you have a blob of size L, for this blob to become, so it becomes ellipsoid, okay? Now there is the decrease of this smaller scale is exponential. So it is kind of the equations. So the main thing to understand is that the flow at these scales is linear. So linear flow has trivial scale invariance. Okay, so if you multiply r by some constant, the flow is multiplied by the same constant. And this is ultimately the reason for scale invariance at these scales, why you have power law. So power law always means that there is some scale invariance, and you must understand what type of scale invariance you have in the problem which you are studying. Here, scale invariance means this. If you consider time for going from some scale L to produce scale L over 2 in linear flow, and you consider the time which it takes from scale L over 2 to go to scale which is L over 4, it's completely the same time. because all distances change according to the exponential law. In this case, it's exponent minus lambda 1t r0. Okay, so there is self-similarity, which is kind of trivial. If you consider evolution, so you study some linear flow, okay? Alpha, well, in our case, it's sigma r. So this is linear flow, which we are considering effectively. Now, you consider evolution in this linear flow of this blob within time t. Say, within time t, it decreased its scale by a factor of 2. The smallest scale became L over 2. Now, if you consider the evolution in this linear flow of rescaled initial condition, then it would be self-similar. Okay, so you simply need to rescale to get evolution of this from evolution of this. This is the scale invariance we're talking about, and this is the reason why the time during which energy is transferred from scale L to L over 2 is the same as the time for energy which was at L over 2 to go to L over 4. This is why this type of transfer from K to 2K is independent of K, which is the reason why we have this power law solution. You see that if it depended on K, it would not, power law would not be solutional. So it's completely essential. Okay. All right. Anybody else wants to help? Thank you, Manor. All right, so let us continue. Essentially, I'm not going to tell you anything which would have much more content beyond what told already. It's simply that if you write a scientific paper or want to provide a scientific argument, you need usually to write a bit rigorously, and this is what we will do. However, the physics will not change because of that. This is all the physics of this power law spectrum. All right, so let me provide you with a formula. All right, so you consider, let me do it in this way. So you consider theta at some point x at time t. Okay. Then you can write that this is theta at time 0, which I will designate as theta 0, at point which is q of t and s. Well, let me maybe, okay, I think well, the reason I'm erasing is that I don't want to introduce other types of Lagrangian trajectories besides those which we had already. So I would need maybe introduce Lagrangian trajectories labeled by final conditions, but I want to avoid too many notations, so let's do it in this way. So as I told you, you have this solution, and at this point, I want us to forget about the forcing, because we have in mind that we will consider actually differences of coordinates which are much smaller than the correlation lengths of the force. So what does that mean? It means that I will, in the end, consider the difference. So I will consider this type of quantity minus theta x. I will have an implication that this is the quantity which I want to consider, because this is what determines the spectrum, all right? So this difference, if you included phi into these considerations, and you would consider here r, which is much smaller than correlation length of phi, you would simply get that phi contribution is negligible. Now, this is, I'm doing it in real space. In Fourier space, this is obvious. We want to consider k, which are much larger than 1 over L, and phi there is simply 0, okay? So I can do everything in Fourier space, but that would demand from me introducing comoving frame. This is how it's done in the paper which you have. I don't want to do it at this point because it can be a bit confusing. Because, well, for some reasons which I don't want to go into at this point. So if you completely neglect the forcing, the solution would be this. It does not mean that we really neglect the forcing. It means that we have in mind considering the quantity which is determined by this solution, which would be where contribution of forcing would be negligible. So in that case, this is the solution. Without the forcing, it's very simple. And you can also consider the solution at point Q of Tx plus W of Txr. And I hope that you remember that Jacobi matrix, so if the point x ends up at Q of Tx at time t, then initial point x plus r ends at the point Q of Tx plus W of Tx times r. And this whole thing comes from the understanding that Q of Tx plus r, which by definition is the position of fluid trajectory of which started at x plus r, you can use Taylor expansion. So this is Q of Tx plus r grad Q of Tx. And this is by definition, grad of Q is W. So this is Q of Tx plus W of Tx dot R. Okay, so this is kind of reminder. So if we evaluate passive scalar at this point, then because it came from x plus r, this is theta 0 at x plus r times the same linear decay factor. All right. So let us then consider the product of these equations and average it over space. Okay, then, so this is reminder. Let me put it in with some demarcation lines. So we continue. We take the product and we integrate over r. So what do we get? We get integral dr, and we divide by volume of space. Theta t q of tx times theta at t q of tx plus w tx dot r is equal to integral dr over omega, theta 0 at point x, theta 0 at point x plus r, exponential minus twice t over tau. Now, at this point, you may wonder why I want to consider this. The reason is that, as I think we talked, the spectrum is nothing but Fourier transform of pair correlation function. So spectrum is integral exponent minus I k dot r average theta at 0, theta at point r, dr. Who does not know this? That spectrum of a random field is Fourier transform of pair correlation function up to normalization. So normalization means that typically you want to consider spherically normalized spectrum. So you divide this property by k square and you get then the spherically normalized spectrum. Who does not know this?
I don't see well, but I didn't know that.
Okay. All right. So what is a spectrum? Okay. So the idea of spectrum is very simple. You want to measure how present given Fourier component is in the field. So you want to have some property of the type average of modulus of theta of k squared. Okay, so this is what spectrum is when you want to get some quantification of this thing. There is, however, a minor difficulty that if you work in infinite volume, in fact, this quantity is ill-defined. It's infinite. Okay, in finite volume, it is proportional to the volume of the system. However, it doesn't prevent us from defining it. You can regularly work with things which diverge using delta functions. So you consider, instead of modulus of theta of k squared, you consider average of theta of k, theta complex conjugate at some k prime. Okay. So then, well, let's take it this way. Okay. So then, by definition, this is integral of dr1, dr2, exponent ik r1 plus ik. Well, usually I define Fourier transform with minus here, so I'll continue that. And the reason is that I think of it as kind of projection on eigenfunctions of momentum, but it's up to you how you think and how you define the sign. It, of course, doesn't matter. So by definition, this is this. Do you agree with this? So we simply write theta of k, which is integral dr1 exponent minus ik r1 theta r1. Theta k prime is exponent minus ik prime r2 theta r2. And then we average both sides. Okay. So then in the case of spatially uniform system, or if you define the average by the as space averaging, so you find that well, this is function of in spatially uniform case, this is function of R2 minus R1 by definition of spatial uniformity. Now, there are ways also to speak of it if you want to define it with the help of space averaging, how you get it. At this point, think simply of statistical averaging of ensemble, which is then you can transform it into something more meaningful, such as space averages. Well, if you kind of do some more work, which if you need, I can show you how you do it. So at this point, please simply ensemble average. This is function of R2 minus R1. And then you get that this is integral of so you can write it as integral dr1 dr2 exponent, and here you can write as minus I k plus k prime r1 minus I k prime r2 minus r1. Okay, so we simply made plus ik prime r1 and minus ik prime r1, and here we have this function of r2 minus r1. So if you pass to the coordinates which are r2 minus r1 and r1, then you can perform integral over r1, And this will give you simply 2 pi cube delta k plus k prime times integral exponent minus I k dot r, or k prime, doesn't really matter here, f of r dr. Okay, so for k prime, so this is only non-zero for k prime, which is minus k, and this is why I'm telling you that this is something which, in fact, in finite system, it's proportional to the volume. You can do it with some calculations, which are not that difficult. Here, I want that you think in the simplest way. So in the simplest way, when you take limit of k prime, which is going to k, the amplitude of this delta function tells you what is the magnitude of component k in the field. And the reason is that k theta of minus k, because it's Fourier transform of real field, it is theta complex conjugate of k, and then this whole thing is modulus of theta of k squared. Okay, so this tells us that this quantity is kind of a good quantity, which tells us how strongly given Fourier component k or minus k prime, it doesn't really matter here. So you can put here plus, so because it's not zero only for k prime, which is minus k, you can write it in this way. So this Fourier transform tells you how strongly component k is present in the random field which you are considering. The divergence is because you consider infinite space, so any so the field doesn't decay at infinity. This is why you get this property here, and it tells you that this is the quantity to consider to decide how strong the given wave number is present in the field. This is the quantity which you actually call the spectrum, which is not spherically normalized, and in fact it depends on direction. So in isotropic systems, which we prefer to consider in turbulence because we have a lot of trouble already for isotropic systems, but in some cases it's not isotropic. So this is the spectrum, and then spectrum which is spherically normalized, you introduce by telling that this P of k, roughly speaking, it tells you density of energy in Fourier space. So if things are isotropic, then it makes sense to assume that this is the amount of energy present at given k can be obtained as a kind of area of the shell in the Fourier space times the spectrum, which is already spherically normalized. And this is the spectrum which you usually see plotted. Okay. All right. So for those who did not know this, these are things which you really must know. It's simply a must when you do random stationary processes. There's no other words, because, well, spectrum is something which people consider all the time. It's not necessary, so maybe it's not completely a must, but it's certainly, whenever you open the book on turbulence, you'll see there the word spectrum. In this sense, you do need to know this. And this is true for any stationary process. And, well, engineers, in fact, know these things quite well. So we want to, this is the reason why we want to consider this pay correlation function, which I unfortunately erased the formula which we had for it, but I'll do it after the break. So we take some 15 minutes break, and then we'll do the last effort to understand power law spectrum of dilute polymer solutions. I think that we are on time for that, so it's going to be fine. All right. So if you have any questions, ask them in the chat. Okay, we continue. We make, so we studied spectrum, which is also quite good. So I hope that Well, I made an effort for introducing as many things which can be useful in your work in this course as I could. So let us use this solution in order to consider the spectrum of passive scalar in this linearly damped case, and then I'll show you how you pass from that to the properties of dilute polymer solutions. Okay. All right, so we write the product and we average it over space. So we have integral dx over omega theta taken at qtx times theta taken at qtx plus w of tx r, and that is equal to similar integral of initial conditions theta 0 at x, theta 0 at x plus r times exponent minus twice t over tau. And this is nothing but the pair correlation function, theta at 0, theta at r. When you write pair correlation function, you don't need to write first argument because it's a function of difference only. So we keep the index 0, indicating that this is pair correlation function at 0 time times exponent minus twice t over tau. So next thing which we do, we use incompressibility. So we can pass from q of tx to from x to q of tx. The Jacobian is 1. So we find that this is integral. So let's designate q of tx by y. Then we have that this is integral dy over omega theta of ty. And here we have theta taken at y, and here we must take a matrix w of tx at point x, which is kind of let me designate it by x, well, tilde, which is determined by the condition that q of tx tilde is y and times r. Okay, so this is something which in fact is not very good. And I was making an effort to do shorter calculation, and it's a bit not what I actually want. So it seems that I do need to introduce the inverse trajectories. Okay, so nothing to be done. Unfortunately, I would need to complicate this calculation. So the reason why I need to do it is that eventually we want to make independent averaging over W and statistics of theta. And when we write it in this way, we cannot actually do it because W depends on theta times T depends on W. And what I want to achieve is actually a similar type of expression, but for theta times 0. So I apologize for this. I wanted to make a shortcut, and sometimes it simply doesn't work. So let us do it. So we do the same procedure, the same solution. However, I must introduce trajectories q of tx, which are a bit cumbersome. So I will, how do I write it so that you can, so let me so introduce it in words, otherwise I would need to introduce many arguments. So this is position at t equal 0 of fluid particle located at time t at point x. Okay, so I can introduce it by introducing third argument into the Lagrangian trajectories, which is not an issue. However, it's a bit cumbersome, so I think it's simpler to understand in this way. So then we can tell that theta of t at time x is theta 0 by definition at point q of tx times exponential of minus t over tau. And we do, so this is our solution. It's the same type of solution. And then what we do is we actually consider the same type of average, but in this way. So we have here that theta of t at x plus r then is given by theta at time theta 0 at point which is q of tx, and then there is kind of Jacobi matrix which is kind of inverse of that matrix. So let me designate it by WR. You can think about it as a time reversed Jacobi matrix. So here this is W tilde, and this is again the consequence of smoothness. So I want to make a shortcut. So I want to, you can find the details in the paper with which you have on spectra of dilute polymer solutions. So then we consider this quantity, which by definition is pair correlation function of theta at time t, at distance r. And using this solution, we see that this is so it is very similar. You'll see why I do this in a moment. So it's integral dx over omega according to this theta at q tx, theta 0 at q tx plus wr. Then you have exponential minus twice t over tau. Okay, so this is where we were heading. So at this point, you again change the coordinates from you pass to q of tx. So you introduce y, which is q of tx. Again, the Jacobian is 1. So this q of tx is essentially flow from which starts at time t and goes backward in time to time 0. So it can be consistently introduced, of course. I don't want to spend time on this because the ideas are simpler to tell than to write in this case. So you find that this is integral dy over omega, theta 0 over y, theta 0, y plus wr, exponent minus twice t over tau. And this is the reason why I needed to switch this frame, which I introduced previously, that we want to make independent average here over space and over w. And we can do it because theta at time, it's very similar reasoning to what we used in order to derive the probability density function of polymer molecule size and turbulence. So the field theta at time 0 depends by causality only, so we consider steady state, okay? So theta time 0 is simply arbitrarily chosen moment of time. Then we consider how the field is transformed from time t equals 0 to some time t, and we demand that the statistics is the same. That is, we have a steady state, okay? We pick this time of evolution t so that it's much larger than Kolmogorov time. So we can use large deviations description of matrix W tilde. It's a bit different. it has completely the same properties as W, which we studied. And in fact, its statistics can be derived from statistics of W. And I'll show you this in the final formula. So then, because statistics at time 0 depends, so W is determined by the velocity field at times from 0 to t. Okay, so it has again the condition that it is unit matrix, this time at time t, because we start from counting in this time from time t and we go back with the time until time 0. And it only is correlated with velocity field at negative times through the last, through this small region of order of correlation time near time equals 0. So we can consider, because that region, it's like neglecting one term in the sum of large number of independent random variables. We had this logic already. Then we can simply neglect the correlation of W with velocity field at negative times. Okay? If this point is not understood, please tell me, because we did have it. So the logic is simple. W is kind of a quantity of this type, which we considered many times. Say, finite time Lyapunov exponents are defined by these integrals over time. So because time is much larger than correlation time, if you neglect in this time interval, so if this is time interval from 0 to t, we neglect tau correlation vicinity of time 0, which is where this process, this W is correlated with velocity field at negative times. Okay, so W again is determined by matrix of velocity gradients in the frame this time of fluid particle trajectory, which passes through x at time t. So the end result of all these considerations is that if you designate pair correlation function by f, then f at time t r, if you average here, so you can make independent averaging over statistics of velocity at t equals is smaller than 0 and over W. When you average over statistics of the flow at negative times, which means the same as spatial average here, you find that this is f at time 0. However, it's taken at point W tilde r. Okay, n times exponential minus twice t over tau. Okay, so the only thing which you need to get from here is that you use the same argumentation to average over statistics at time 0 and statistics of Jacobi matrix at later times. And then you have that the pair correlation function is transformed in this way with certain matrix W tilde, which, as you can guess, is very similar to the Jacobi matrix which we studied. In fact, it's simply the Jacobi matrix of time reversed flow from time equal t to time equals 0. Okay, so the next step is to consider the spectrum, which, using our definition, is integral exponent minus I k dot r f of r dr. Now this f does not depend on time in the steady state. So in fact, when we write this first argument, this equation is true. However, in the steady state, there's simply no dependence, explicit dependence on f. And we will, of course, use it because we want to write steady state solution, steady state condition. So, as I told you, we neglected the forcing in this consideration, which is not completely true when we consider pair correlation function. However, you can easily see that Fourier transform at finite wave number is the same for difference and for product. Okay, so if you consider difference of theta at nearby points, its Fourier and square it, its average is proportional to the Fourier transform of pair correlation function. Okay, this is simple exercise which you can do. So let me show this very shortly. So theta of r minus theta of 0 squared, which is the quantity for which you don't care about the forcing, because you consider scales much smaller than the scale of forcing, and you remove the uniform component, which is kind of due to that you can see due to the forcing, that you simply open the brackets, and what you find is that this is twice theta squared minus twice theta 0 theta r. So what this tells you is that if you make Fourier transform of the difference up to factor -2, it's the same as Fourier transform of pair correlation function, because Fourier transform of a constant is delta concentrated at 0 wave number, and as long as we consider the Fourier transform at finite wave numbers, this term simply does not contribute, and difference and pair correlation functions are proportional. Okay, so this is the reason why we have the right to remove the forcing on the level of formulas. So again, if you derive things, you carefully write everything, and the best way to do it is to pass to comoving frame as it is explained in the paper. So we have this equation that f of r equals f of this w tilde r times exponential minus t over tau, twice t over tau, and it has very simple meaning. So all distances change according to some Jacobi matrix. So you take distance at time r at time t, then the distance at time 0 was some linear metric, some matrix times distance at time t, and then there is this decay, linear decay factor. So it's very straightforward equation, and when you make its Fourier transform, you find that. So Fourier transform of this gives you simply E of k, and Fourier transform of this gives you exponent minus twice t over tau. And here you have spectrum. Well, let me make this step. So you have integral exponent minus I k dot r f of w tilde r dr. We pass to new variable, which is w tilde r. Again, the Jacobian is 1 because the flow is incompressible. So we find that this is equal to exponent minus twice t over tau integral exponent minus I. Here you can write it as r prime dot w tilde minus 1 transpose acting on k. F of r prime dr prime, where r prime is w tilde times r, and this is transformation which has unit Jacobian. And this is nothing but the spectrum taken at w tilde minus 1 transpose k times exponent minus twice t over tau. Okay, so with all the complications of this derivation, which is the expressions are long, it's not complex, but it's simply has long expressions. You find the same equation which I told you previously, that spectrum at some k equals to the spectrum which was to the energy at k at time t equals energy at time 0 concentrated at this point times exponential decay factor, where this wave number is actually the wave number from which the energy came because of this advection due to velocity field. And then you can actually write this matrix W tilde as it's explained in the paper. It's writable in terms of W, the Jacobi matrix which we had before, and the actual equation is one moment. So it's okay. All right, so this is exponent. In fact, W tilde is W minus 1, which makes sense because so W tilde is W minus 1, which of course makes sense because W realizes transformation of distances from time equals 0 to t. And we want to make transformation of distances from time t to 0, okay? So that is what is done by matrix W minus 1. So W tilde transforms distances from time t to time 0, and that is W minus 1. So we find that in terms of our matrix W, which we studied so well, we have that this is W transpose K exponent minus 2t over tau. And now, what is the difference from this equation which we spoke about before? So I gave you previously the equation that E of twice K is E at K times exponent minus time of transfer divided by tau. Now, in fact, because it's square, here it must be minus twice time of transfer, which is not a big change, of course. It's simply, it didn't make sense to write that factor of 2 when we had order of magnitude estimate there. So where do you see it here? Now, this point is not completely trivial, so let us understand it. So, in fact, the time of transfer from K to twice K is not some deterministic given number. It is random time because the flow is random. So the time it takes to transfer energy from K to 2K is by itself a random time. So this is why if you specify here that WTK, which is our initial wave number, by modulus is equal to K over 2, then we would get that this time, which we need to use here, is not a fixed number, but it is by itself a random number. So we do not actually solve the equation in that form because it's less convenient from the viewpoint of formulas. However, from the viewpoint of calculations, and of course here we have still the average over W, because we averaged only over initial statistics and not over statistics of W. So if you specify that W T of K is K over 2, you can do it, but then you would have here exponent of minus twice T times time of transfer, which by itself is this time random quantity, and you would need to speak about this time of transfer. You can do it, but it's not the simplest way to make this derivation. Why I write this form is because I want that you see the connection with the derivation we had before. It is the same, but mathematically it's simpler to work directly with the equation in this form. And the remaining thing is to determine that indeed the solution is a power law. And here I would like to hear you. So please let me know how we prove that this equation has a power law solution for the spectrum. So do you understand the question? So we derived this equation for the spectrum, which I hope that you understand. So distances transform in a way which is conjugate to wave numbers, which is more or less what we did here. And we got this equation. So there's something written in the chat. Let me see what's there. Okay. So Pavel tells that it's understood. Okay. However, so what I wanted to show that you show at this point is that this equation has a power law solutions and how you determine the exponent of that solution. Okay. All right. I give you some time. It's as simple as it can be. Okay, so this is the equation on some unknown function. I'm telling you that this equation has power law solutions and request you to tell me what, how you determine the exponent of that solution. Okay, last effort. No more questions.
I mean, you can look for self-similarity, or you do something with dividing the logarithm of your spectrum over the logarithm of k, something like that. Then you should get the power spectrum, or like the exponent, or like the power coefficient, or?
Okay, so what do you do with this equation? So this equation tells you that E at wave number k equals E at W transpose k, where W is some random matrix, times exponential of minus twice t over tau, averaged over statistics of this random matrix. So how do you do these things which you're telling? So what do you do? What's the next step?
I mean, isn't it this already some form of self-similarity?
It is. That's what I'm actually.
I mean, you just need to know. I mean, it just shows how you get from somehow transform k to a new k, essentially, or?
Yes.
So you can essentially look at the ratio of those two. Or doesn't matter?
Yes, more or less. However, this is something which we saw in a bit different situation where we considered equation on probability density function of logarithmic variable of turbulent of polymer extensions. So you simply put the solution, which is c to power k to minus alpha. You plug it into this equation, and you see that constant disappears and k to power minus alpha disappears. And you get the condition that average of W transpose acting on unit vector k to power minus alpha times exponent of minus twice t over tau is equal to 1. And so this is what I requested. It's something simple, how you derive the condition on the exponent from this equation. And it's not only to show, to write this condition, it is actually something which allows you to tell something about this alpha. So you see that this is very similar to this generalized Lyapunov exponent which we considered. And in fact, you can write it in that way. So you can introduce generalized Lyapunov exponent as W transpose k to power p, which gives you exponent of gamma p times t, where gamma of p has the same property as we had before, that it is 0 at minus 3. Simply you use matrix W transpose instead of W. And you can show that there is no difference whatsoever in the form of this function. Its general properties are the same. And then this condition gives you that gamma, well, let's call it gamma tilde because it's different. Gamma tilde at minus alpha must be equal to twice over tau, okay? So this is a condition which determines alpha. And from this, you can actually show that alpha must be larger than 3. And the reason is this, that either this is positive here, but then you can show that it's not physical solution. So maybe it's the other way around, but you show in the end that alpha is larger than 3 by similar argument that must be, it's positive either here or here. That you can read in the paper. In the appendix C there you derive this inequality. So the end result of all these considerations is that the spectrum obeys the condition, obeys power law form with alpha larger than 3. And this condition is significant because it's also, for polymers, it tells you that indeed, self-consistently, the gradients are determined by the scale R star. So the last thing in our lectures is how you pass from passive scalar to actual spectra of dilute polymer solutions. And this is fortunately straightforward, though cumbersome. So you need to do something which is quite, well, you need to understand that you can do it. You actually decompose the fields into the large scale component and small scale component. Now, what that means is that you simply write that B tilde is integral exponent I k dot r B of k dk over 2 pi 3, where you consider k which are smaller than some 1 over L. So this is large scale component. It involves only small wave numbers. And you have also small scale component, which is B prime, which is integral over k, which is larger than 1 over L. So you kind of write Fourier representation of B as sum of contribution of wave numbers smaller than a given one and then larger than a given one. And then you find that actually B prime obeys passive equation in the large scale field. And that equation, so it doesn't interact with the large scale flow. So B prime is passive, and then you can derive its spectrum, which means to derive the spectrum at large wave numbers, and properties of B prime are not very different from passive scalar. So you can read the details in the paper. I hope that you understand the idea, and that's what I wanted to transfer here. So we have some minutes. If you do not have any questions, so if you have any questions, please ask them. All right, so I'll send you, there is some form which I must send you so that you evaluate the course. I hope that it was, you learned a lot here. And I thank you for listening to this and for staying for so long. I will be able to interact with you, and if you write me some email with remarks or questions on the course or whatever, I will be glad to answer. Thank you for your attention, and well, let me show my face. We finish. Thanks.
Thank you, Itzhak.
Thank you.
I'm glad that we had this
Thank
COVID
you.
stuff. So we did it online, and we can revisit the course, because I think it's worth to revisit this many days. There's many in-depth things on advanced turbulence and mathematics. So I think I'm glad we had this recording at least to revisit it. Thank you.
You're well welcome. Thank you. Thanks.